Hello everyone, this is Mike Dowding, and this is a test video using a combination of OneNote and screen capture. And I'm going to make a short little video here, as I said, just to test the software and to see how it gets out to you, the students, see how well you like it, and I want to hear back from you to see if there are any improvements that can be made, because this is more than likely going to be the way that we're going to be having lecture from here on out. So what I have right now is just OneNote opened up. I am going to, well, I've already engaged the video component of the screen capture, but what I'm going to do is I'm going to go through one of the homework problems from Chapter 6 in its entirety until we get to a solution. That homework problem in particular is the sliding pig problem. So in Chapter 6, I think it's the first homework problem on the set, where you have a pig that is sliding down a slide, actually two different slides. One of the slides has no friction, the other slide does have some friction, but I'm trying to get my screen to flip over here. It doesn't seem to want to be working, so I'll just flip my laptop around. So what we have is a pig that's going to be sliding down two different slides. So first things first with our problem-solving process is we will draw ourselves some inclines. One incline is going to be what we call the no friction case. And the other incline over here will be the friction case. And I'm going to shorthand these as NF and F. Now, even though these inclines look a little bit different, these are going to be the same slides with the same inclines of theta. We're going to have the same pig sliding down each slide, and instead of trying to draw a pig, I'm just going to draw a box of mass M. And in each case, these pigs are going to start at the top of the slide with some initial velocity that is 0. They're going to slide down the slide, and the only information that we are given is the value of theta. And given the different theta values that can pop up with all of your different Wiley Plus homework sets, let's just say for this case that theta is 30 degrees for each of the inclines. What they want to know is, in the case of the friction slide, what is the coefficient of kinetic friction? If it takes twice as long for the pig to travel down the friction slide as it does the non-friction slide. So right here I've just written down that time for the friction equals twice the non-friction time. So over here, whatever time it takes for the pig to slide down the incline, that's going to be TNF, which, to generalize things, I'll just call that T, which means the time in the friction case will be 2 times general T. Now, with everything that we have here, there's a lot of unknowns, which can be a bit overwhelming, including the fact that we were not told the mass of the pig. And this is a problem dealing with friction, which is a force, and force requires the second law, F equals ma. And so how are we supposed to do this without the mass of the pig? Well, as was mentioned in class a couple of times, if there's a value that you're not given, you probably don't need it. And as is the case with the time for the pig traveling down each slide, they did not give us the time that it takes the pig to travel down either slide. And so we probably don't need to know that, but we might want to know the fact that it's taking twice as long to travel down that friction slide. So here's what we're going to do. Since we have so little information, let's take a look at exactly what information we don't know. We don't know the mass of the pig, obviously. We don't know the time for either of these cases. We don't know the coefficient, which is the only thing really that they're asking for. The only thing that we know for sure is our theta value. This is nonetheless going to be a force problem. And when it comes to force, we can use force to help us figure out what the acceleration is going to be. So both of these pictures have a pig, and the pig is going to be subject to different forces, which is going to cause the pig to want to accelerate down the incline. So in each case we have acceleration. There's acceleration of the pig with the friction case. Here's acceleration of the pig with no friction. And one more thing I'm going to put in here. Remember that these slides are identical with the exception of the friction, which means in both cases the pig is going to be sliding the same displacement down each slide. So now we want to put all of this information together. And the way that we're going to do that, if you notice, I have a lot of terms on here that look like they come from a kinematics problem. So let's see what happens if we try to put everything together in a kinematics problem. So in the case of non-friction and in the case of friction, we have initial and final velocity, acceleration, displacement, and time. Likewise for the friction case, we have initial and final velocity, acceleration, and time. Now these values are slightly different because of the friction, but we do know that the initial velocity is going to be 0 in each case. We don't know how long either of the slides were, but we do know that they're the same length. And so what I'm going to do is I'm going to put in that unknown value of displacement for each of these. And this is, of course, assuming that the pig is traveling in the positive x direction for each slide. So I'm just going to go ahead and set up a reference frame. It's the same reference frame for each one, but now this will allow me to label what is positive, what is negative, etc. So in both cases, the pig is sliding down the incline with a displacement of positive d. we know that the time for the non-friction case, oops, gotta switch my color back over, is generic t, and the time for the friction case is twice that amount. The one thing I have absolutely no idea about is how fast the pig is going to be traveling when it gets down to the bottom of either slide, because in each case it's a different acceleration value. The pig is going to accelerate down the slide at different rates because of the inclusion or absence of friction. So if we can figure out what the acceleration is for the pig in each case, then maybe we could build a system of kinematic equations which would involve both the generic displacement and time values, along with the acceleration and the initial velocities. And even though I don't know what these displacement or time values are, maybe I can set up my system of equations in such a way that they will cancel out. And then I can solve for something in terms of the acceleration, which, remember, F equals ma. Our friction force is going to give us some information about what the acceleration in the system is. So we'll go back to the pictures, and I'm going to draw a fresh set of pictures here because the pictures up top are getting a little messy. So in the non-friction case, we have our pig, which is sitting on the incline, getting ready to slide down, and the forces that are acting on the pig are the weight of the pig, mg, pointing straight down. There will be a normal force pointing normal to the surface. The acceleration of the pig is downhill, which means that our friction force will be uphill. Everything in the problem statement implies that the pig will start to move, so we don't have to waste any time trying to figure out how much maximum static friction there is. All we need to do is figure out what is the balance of these forces. And up above we said this was going to be our XY axes. I'm just going to clean that up. There, that's much better. So the next thing we want is a sum of forces in each direction. Because of my choice of reference frame, there is only one force in the entire system that has to be broken up, and that is the weight. And so the weight will need components along the x and y directions respectively, which are actually parallel or perpendicular to the incline. Then we need to incorporate the angle from the incline, theta, but that's just going to go in this top corner here. And this is something that we've seen in multiple examples in class. So now we're ready to go. We're ready to put together the sum of forces. In the x direction, we have the component of weight, which is pointing downhill in the positive x direction. And then we have the kinetic friction force, which is pointing uphill. That's the negative direction. And that's it for the x direction. So these have to get together, and these will tell us how our mass accelerates down the incline. We need to know what that static friction force is. And from our definition, F sub k is equal to mu kn. N is the normal force. And, well, we don't know what the normal force is, so we look back at the picture. The normal force is in the y direction, so let's take a moment and produce the sum of forces for the y direction. We have normal up. We have the other component of weight down, and those two are going to have to equal 0 because we don't want the pig spontaneously flying off the slide. The pig has to remain in contact with the slide at all times, and so that means that our normal force is equal to mg cosine. We bring that up to our friction equation. Mu kn now equals mu kmg cosine theta, and that will be substituted in for f of k. So we need some more room. Our sum of forces expression in the x direction so far is mg sine theta minus mu k mg cosine theta equals ma. Ah, that's a lot. But now we can see one of the outcomes that we were hoping for. And if we go all the way back to the beginning of the problem, we said, well, they didn't tell us what the mass of the pig was. Well, that's because we don't need it. Because each term in this expression has the mass of the pig, which means we can cancel out the mass of the pig. In fact, the nice thing about this software is I can just remove it. What's left here is an expression that tells me how fast that pig is traveling down the slide, and right now I can see a mistake that I made. I said that this was going to be the non-friction case, and I went ahead and put in friction in the problem. So let's just make an amendment there and say that this is the friction slide. And we can come back and do the non-friction slide here in just a few minutes. But so now I have the acceleration of the pig as it's traveling down the friction slide. It's all of this, but I can clean that up a little bit. I'm going to factor a g out, which leaves us with sine theta minus mu k cosine theta, which is good because now I actually have the coefficient mu k in one of the expressions, and that was what we were asked to solve for. So this acceleration value is going to be plugged in right up here. We have g sine theta minus mu k cosine theta. And you might be thinking to yourself, well, alright, I've got 1, 2, 3, 4 values that are going to go into a kinematics equation. Let's use those. But remember, I don't know what these two values are just yet. I'd like to get a little more information about the system. And to do that, I need to depend on this comparison between the times. I know it takes twice as much time for the friction case, so I might want to get some information about what the acceleration in the non-friction case is. So now to the non-friction case, and this time I'll actually do a non-friction case. Now as far as the pig is concerned, everything about the forces is the same, except there's no friction force. We're still expecting the pig to slide downhill. We have the same normal force, we have the same weight, we have the same theta value. So when it comes to figuring out the sum of forces for the pig in the non-friction case, well, I get the exact same normal force as what I got before, except now all of this is useless because up top I only have the downhill portion of gravity, which is responsible for accelerating the pig. And once again, I don't need to know the mass of the pig. I just get that the downhill component of acceleration is g sine theta. So all of this down here was useless. But this is now the acceleration of the pig in the non-friction case. So we're going to bring that up here. And we'll plug that in. And now, believe it or not, we actually have everything that we need to solve for mu k. Now, to help us out, I'm going to clean this up a little bit. I think I'll come over this way. And I'm going to produce some kinematic equations using the values that we have in each set. So I'm going to take those four values, plug those into a kinematic equation, and, well, as it turns out, I'm going to use the same four values from the non-friction case and plug that into a kinematic equation. Because I'm using the same four values, I can just use the same kinematic equation for each. And the kinematic equation I want is the one that leaves out the final velocity. So we look at our list of kinematic equations. The one that leaves out final velocity is delta x equals v naught t plus half at squared. And we're going to apply the information from each case to that equation. So in the non-friction case, the kinematic equation will have I'm trying to change the color here. So we're going to plug those four values in. Over here. So delta x, well, delta x was the displacement, and that was d, equals the initial velocity times the time. Well, the initial velocity was 0, so that term goes away, plus 1/2 of the acceleration of the pig in the non-friction case times the time of the pig in the non-friction case. So the time that we had for the pig in the non-friction case was just t. The acceleration for the pig was g sine theta. So there's our equation for the non-friction case. We need to compare that to the same equation using the information from the friction case. In the friction case, the pig still slid a displacement of d. It still had an initial velocity of 0. But here's where things get different. The time for the non-friction case was twice as much as the friction case. And up here in our equation, that time value has to be squared, which means we're going to end up with 4t squared from that from that last parenthesis set. Inside the other parenthesis set is going to be our other acceleration value. That is the acceleration of the friction slide. So that was g sine theta minus mu k cosine theta. And it's starting to look like a big mess here, and I agree. But let's just see what we have. Here is d equals, now the 1/2 out front will combine with the 4 at the end of the statement to give us a 2. We have g from inside the first parenthesis set. We have sine theta minus mu k cosine theta, all followed up by that t squared term. From the non-friction case, we have 1/2 g sine theta t squared. And now is where our life is going to get so much better, because each of these equations is equal to the same displacement value, d, which means we can set these equations equal to each other, because d has to equal d. And the moment we do that, a lot of other stuff starts canceling as well. First thing that we see that's going to cancel is our t squareds. Another thing that's going to cancel, whoops, I lost my my theta value there. That wasn't supposed to go away. Another thing that's going to cancel out are the g values. So apparently we don't even have to be on Earth for this to happen. Next, I'm going to take that 1/2 on the left, and I'll multiply the 2 over to the right-hand side. And when I do that, I'll get a 4. And just to recap as to what we have a 4 sine theta minus 4 mu k cosine theta. And now you can see that we are in line to get our solution for mu k, because the only other values that we have in this system are sines and cosines of theta. And theta was the only thing, the only piece of information that they gave us. So here we go. I'll subtract a 4 sine theta from each side. That's a -3 equals -4 mu k cosine theta. The negatives on each side will drop out. And I'll divide each side by 4 cosine, and that will give us 3/4 of tangent equals mu k. So there's our answer. Regardless of who you are and what value Wiley gave you for theta, we now have the coefficient of kinetic friction for the friction slide. And it's at this point now we can plug in our value of 30 degrees and calculate what our answer should be. So we're going to get our calculator out. In my case, I'm going to open up the calculator function on my phone. So tangent of 30 degrees times 3/4 equals, and I'm getting 0.433. And the coefficient of friction is just a coefficient, so it is unitless. And I realize that this probably seems like way too much to do for a single homework problem. And I would agree, especially given the amount of detail that I've shown for this. But this is an excellent example as to why so many of our physics problems, homework problems, etc. should be done in generic form. In other words, you should have general information that leads you to a general solution. And we quite literally did not have a choice, because they gave us no information except for theta, yet we were able to use almost everything that we have seen and heard this semester to get us from the start point to the solution. And so regardless of whatever physics problem we are presented with, we should always be able to produce a general solution and then plug our numbers in. Plug numbers in. Alright, so that brings us to the end of the problem. We have our answer, and so that brings us to the end of the video. Hopefully the sound quality on this is okay. If not, I think I'll run down to the store and purchase myself a headset with a microphone on it. Otherwise, I'm going to send this video out to a handful of students just to get some feedback, and that should do it. Have a good day.